Okay, now let's start talking about the Gaussian filters. And Gaussian filters are generally based on the equation, which is g, and this would be 1 over 2 pi sigma e raised to power minus x square over 2 sigma square. If you generate, for example, a 5-tab filter, so its values would be 0.029, 0.235, 0.471, 0.235, and 0.029. However, since we know in our images the values are whole numbers, so the filter that we generally use would be of the form 1, 4, 6, 4, and 1. And then we would be normalizing it by 1 by 16. Similarly, if we are going for a 2D filter, so it would be 1 over 2 pi sigma square e raised to power minus x square plus y square over 2 sigma square. So in order to generate this filter, what we do is that we multiply g of t with the g. So this would be giving us 1, 4, 6, 4, 1, and then 1, 4, 6, 4, and 1. And if we do the respective operations, so our 5 by 5 2D kernel or the filter would be 1, 4, 6, 4, 1, 4, 16, 24, 16, 4, 6, 24, 36, 24, 6, which would be followed by 4, 6, 4, 16, 24, 16, 4, and then 1, 4, 6, 4, 1. Of course, we have to carry the normalization factor, so it would be normalized by 1 over 256. So if you use this filter for before basically applying the decimation, so the jumps that we had seen along the x-axis, along the column, or the y-axis, along the rows, would actually be reduced, but we are actually using more computational values, computational cost. So our decimation system would be looking like we have x, so this would be passing through low pass filter. In present case, it's basically Gaussian. Then we would be doing the decimation, and finally we would be having the x of d. So this factor could be an integer based, or it could be fractional based. So here we have seen an example of decimation by 2 along the rows and column, so basically symmetrical 2 by 2. So this could be 3 by 7, let's say 3 by 7 as well. And previously we already have seen examples for this type of the operation. Thank you.